Hello folks, well welcome to a very quick entry for the Flashing Light Prize 2018. This is, well maybe it's going to be annual now, I don't know, but there was one last year, or this year should I say, in 2017, and the idea is that you present on YouTube, for example, a video showing a flashing light. Now last year it was, the limitations were a little bit less specific than this year. This year is a little bit different because we have to use a neon. The way of actually getting the light has to be maybe a bulb or a tube or whatever. It has to be a neon-based emission or light based on neon gas. So that does limit you, and then there's a few more bits and pieces in here which I'm going to draw your attention to, and one of them is that if you go down here a little bit further, the flash rate must be 1 Hertz. Last year it was between about half a Hertz and 2 Hertz, so you could have all sorts of weird and wonderful mechanical and whatnot gadgets which didn't have to be too accurate. So this year it says it has to be 1 Hertz, so I don't know how accurate that has to be, but let's say to within, I don't know, 1%, or well, maybe better, it doesn't actually say specifically, but let's say within about 1% or so is good enough, and a 50% duty cycle, so that means it's got to be on half the time and off half the time, so that again makes it pretty specific. And you've got to be able to operate it for 1 minute without it breaking down or, well, exploding. So I should just draw your attention to something here. Now normally if we think of neon bulbs in their sort of classical sense, you generally, if you want to light them from electricity, and this isn't saying that you have to use electricity directly to light them, there's possibly other means as well, possibly RF if you want to do that, radio frequency energy. I don't know, that's not something that I know anything about. The only background I have with neon is many years ago and using them as mains indicators. They're essentially a precursor to indicators like LEDs that we have nowadays, but LEDs are a little bit easier to use, they're much lower voltage, whereas neons, I'm afraid I'm going to have to tell you, neons are high voltage, so we need to be careful with that. So I'm just going to let's go through about neon bulbs, which is what I'm going to use here. And you probably need around 90 volts, possibly more, depends on the actual device. Certainly the little ones I'm talking about. I'll show you here. These are maybe the size of a small pea. These are very large grain of rice. These are the devices that I'm using. Not sure if I can zoom in a little bit on that. And that's the neon bulb that I'm talking about. So inside it there's 2 electrodes, and this little bulb has some neon gas in it, probably for quite low pressure. And by putting a voltage across here, you can make it illuminate. So I managed to get a whole bunch from eBay, just purely because of this particular flashing light prize here. And so let's zoom out a little bit here. Here we go. So I managed to get, you can get them for even cheaper than this, but because I'm quite impetuous, I decided I need to get a load quickly. So these took a couple of days to arrive from a UK source. And sure enough, 100 of these things turned up a couple of days after ordering them. I think you can get them down to probably less than half that price if you order them from China, Hong Kong, and whatnot. So a couple of other things. So although it needs 90 volts to turn on, you don't need much current. About 500 microamps or half a milliamp is enough really to them to remain on. And also once they actually turn on, the voltage across them doesn't have to be 90 volts. It can be a little bit less. However, for the purposes of what we're going to do here, I don't think that's particularly a problem here. So this is my design. It's not particularly smart or clever or anything like that, but I'm just going to run you through it quickly. So first of all, we need a 90 volt power supply for this. Is the neon bulb here. You need a 90 volt power supply, and you need some sort of a switch to turn it off and on. Now, one thing that you do need to do as well is to put a current limiting resistor on here. So we'll go into the detail of that in a moment. But one thing I'm just going to just say again and again in this video, this is 90 volts, and you've got to be real careful here. So let's just be really clear here. If you don't know what you're doing, just don't even go there. But I'm going to reiterate, this is high voltage stuff here. So my little thing wants to run off a 1.5 volt AAA cell. So that's kind of interesting, because you're trying to get 90 volts off a 1.5 volt battery, and then there's not really much that's particularly clever here. Could use all sorts of things to generate a 50% duty cycle. I've got a microcontroller here, because I can make it fairly accurate with that microcontroller, generate the 50% duty cycle. The only problem is microcontrollers, most of them don't run off 1.5 volt cell, and as this 1.5 volt cell drops, because although they're marketed as like 1.5 volts, over a period of time it actually drops a little bit, and so you need some sort of power supply to create enough for the microcontroller. Now normally you can get microcontrollers quite easily that run off about 1.8 volts, but I just went for 3 volts because I happen to have the microcontrollers I have in stock easily run off 3 volts, or even 2.5, but I've settled for 3 volts, and let's go for that. So you need to have some means of generating this 3 volts, so we'll go into that as well. So that's the basic premise, 1.5 volt cell, and what I'm going to do in here is I'm just going to show you, this is our circuit, and this is it. And I'm going to pop in, hopefully we're going to be able to see it actually light up. So yeah, I think we can. So you'll see this is the neon bulb, and if we go in very, very close, you'll see that only one of the 2 electrodes is actually lighting up. That's because we're putting DC. If you're at all familiar with the mains indicators, both of these light up, or appear to. It's just because you're going through 50 Hertz backwards and forwards, positive, negative, so that will light up both of them, or appear to, but on our persistence of vision makes it look as if both of them are actually lit up, but there's actually only one of them. If you look probably more from the corner of your eye, you can actually see them flickering a little bit as well, so there you go. So you'll notice also on this board I put 100 volts DC danger signs on here, so I will come back to that later, but I'll leave this just sitting here by the side, and hopefully it'll keep going throughout the length of this video. Right, so question is, I guess first of all, is how do we generate 90 volts from 1.5 volts? Well, we could use a boost converter. The only thing is going from 1.5 volts to 90 volts, probably going to need a transformer, some sort of coupled inductor to do that. I don't happen to have those in stock. One little thing for safety, I put a little switch on here, you can see that here. So I could test all this bit without having 90 volts all over the place. Just one thing further to note, this power supply's got capacitors in it, so even if you switch it off there could still be quite a high voltage on this rail, so you need to leave it a minute or so for it to dissipate out. So let's go through and talk about our 90 volt power supply. Well, this all looks quite complicated, doesn't it? So what I'm going to, let's just zoom out a little bit so we can get everything on here. There we go. Yeah, you still see it flipping away there. So this looks kind of complicated here. What is going on? Well, the reason why this is complicated, or looks complicated should I say, is that I was thinking, how am I going to generate 90 volts? Now, this is quite an interesting circuit here, which is an application note from Linear Technology, number 47, and in the appendix here you've got a circuit which has become a little bit of a classic in its own rights, to be honest with you, by Jim Williams, and this is based on a boost converter and then a charge pump afterwards. So it uses the unsmoothed boost converter to so it's still switching just here. Normally what you do on the output here is you just use a capacitor just to couple it to make it so that you've got a nice DC voltage. And whereas what's here is that they've actually taken the advantage of this is still oscillating here. Now you might say, why can't we just generate 90 volts straight away? Well, we could do, but again probably would want to use coupled inductors. But more importantly, the maximum voltage that can appear on this SW1, the switching output, this is a transistor switcher internal into this chip here, is 50 volts. It's an LT1073 for those watching at home. You can see the maximum voltage on SW1 is 50 volts. So we can't generate 90 volts right off the bat off of here. We have to use a charge pump mechanism here. And you can look up charge pumps, but basically if you've got an oscillating voltage, normally a square wave, what you can do is you can use diodes and capacitors in order to be able to generate a higher voltage. Quite neat, and in low current applications they're quite common. Say for example providing negative bias voltages, so you can do positive and negative with them, but the output of them isn't regulated. So let us discuss this bit more completely. So you'll see there's a lot of similarities between the Jim Williams power supply, which was used for a different reason. Almost everything here around this LT1073 is the same. Again, we've got our switch here because want to be able to switch this off while we're messing around with other bits on the board, and I've laid it out in the way that the chip pins come out. Frankly, I find that a little bit easier to do it that way. When I'm just showing a diagram like this, sometimes I use the more symbolic representation. 150 microhenry inductor. I just use one that I happen to have from a lab kit. It's a Coilcraft one here. Here we go. Happens to be in a kit. I'm pretty sure that you can get away with a 100 microhenry one. I'll just show you a little bit more on the specs on this. This is the spec of the Coilcraft one that I had. I'm sure that other ones would do just as well. And then this is the charge pump here. Now I couldn't find any ceramic caps in stock which with sufficient voltage to do for here, so I've used electrolytics, and so this is 0.47 microfarads or 470 nanofarads. Bear in mind the switching frequency here is probably about 10 kilohertz or something of that order, so you don't need massive capacitors. And these diodes, because it is about 10 kilohertz and need to be reasonably fast rectifier diodes, these again were just what I had in stock. I'm not sure if the 1N4000 series would be fast enough, but don't go for the base one, because the 1N4001 is only about 50 volts. So I would go for 100 volts plus rectifier diodes. Bear in mind you've got 90 volts DC on here. Even though I think these are only actually switching maybe 50 volts anyway, whatever. No harm, 100 volt rectifier diodes, fast recovery. And so then also we need to say, well, what's happening? How do we get this regulated reasonably well? So what I've got here is, again, this is from the Jim Williams design, 10 meg and 22k, and I think the reference voltage is about 0.2 volts here. So we get a little bit over 90 volts DC out here. Again, danger everywhere here. No touchy. Okay. So now I've gone through that, we need to, let's go back to the diagram here, and we can see that we've got a 3-volt power supply and a microcontroller and some sort of way to switch. So let's see what we've got here. So for the 3-volt power supply and the 1 Hz oscillator, I mentioned I'm using a little microcontroller, so a few milliamps max. In fact, the device I'm using is only taking about 50 microamps. I think it might even be less than that, so it's nothing really. I'm only running it at the internal low frequency oscillator, about 31 kilohertz, which is very, very slow for a microcontroller, but it's good enough for what we're doing here. So we don't need a very high current here, and we'd like it to be regulated, thank you very much. Not strictly necessary in here, but I decided to say, you know, for good practice, let's do a little bit of over-engineering. I think if you were going to do this as a cheapo product, well, whatever, you probably wouldn't bother with it being regulated for what this is doing. In fact, you probably wouldn't even use a microcontroller. There's nothing like a bit of over-engineering, is there? So if you want to use low current, typically a charge pump is quite a cheap way to do it, because it means you don't have to have inductors. Inductors are expensive devices, so tend to try to avoid them from an engineering perspective. So charge pump sounds good, but they're not regulated, so we need a charge pump plus a regulator. So now we could do that with just a normal charge pump, either a chip or make your own, or alternatively what you could do is you could find a device that does that all for you. Now I happen to find that the Texas TPS603XX series seem to provide that functionality. So I'm using a TPS60313, which delivers a 3-volt regulated output at about 20 milliamps, which is more than enough for our application. And this is how this works. Again, I've done it on a pinout. Now, one thing just to keep in mind, this is in a 0.5mm pitch device, so you're going to need probably a breakout, or either that, or if you want to do board layouts and whatnot, then yeah, you probably want to think a little bit more about how you're going to do this if you don't like really fine pitch stuff. So a bunch of 1 microfarad ceramic caps around here, just Y5V series would be fine for this. Not really particularly important about keeping the tolerances there. This is our same 1.5 volt supply, it's just here, just unswitched. As I say, that same 1.5 volt supply here as in here. It's unswitched here because we want to be able to test this bit without having to have the high voltage around, just for the purposes of keeping our fingers safe. And this is the microcontroller bit. So this is a PIC16F18313, bit of a mouthful this. I did actually look to see if I could get a microcontroller working which was a PIC10F. I could do that, and in fact I've done that previously for last year's flashing light prize. I decided not to do that for this particular one, really because you'll see that this is actually in a socket. Reason being is that they've got high voltages here. If I blow something up, I'd rather just lift the thing out of the socket than have to replug it in. And in fact, the 10F series, if you want to get them socketed in dip sockets, they're in 8-pin dual-in lines anyway, so I just went for that. PIC10F18313 also has got better debugging facilities on chip, just a more modern chip. I did look at getting a 10LF or a PIC16LF, which is the low voltage versions. They go down to 1.8 volts, and I was wondering if I could get away without that. Unfortunately, it didn't arrive on time, so I went with this instead. So we've got a 1 Hz output here, which will be push-pull output, so it'll go down to ground and up to 3 volts. So we need to have, the problem is we need to switch 90 volts, so we're going to have to use something like a transistor to do that. So I've got a transistor in here, which is in a SOC23, so a tiny little thing, and I'll go through that on the board when we in a moment. And 47k, this is our current limiting resistor on the neon. This is on 90 volts, so no touchy. And just make sure that your transistor is 100 volts at least. I think this one's actually about 300 volts or something. Doesn't have to be massively high current. This one's half an amp. This is probably overkill. Now there's one little thing here which I made a little modification from my original. Originally I had a 10k in here, and what I noticed was that the peak current at the 1.5 volts here was actually quite high. It was going up to about 120 milliamps, and I was thinking, well, if this cell starts to deplete a little bit, it's going to struggle flashing. So what I did was, in order to reduce the the very quick on which happens here, what I did is I put 100k in here, and what that does is when this first switches on, there's a reasonably high current goes through here. When it starts to switch, when it initially switches on, then it relaxes. As I mentioned earlier on, right in the beginning, that although you need 90 volts to turn it on, it go down to about 70 or so, 60 or 70, and it'll remain on, perhaps even less than that. So what this 100k does is that it just sort of limits the current, and what it does is it means that as this sort of gradually goes up, so it gradually closes here, this doesn't get a big, if you like, clamp, not so much a clamp, but it just reduces the amount of, in the end, the amount of current coming through this 1.5 volts to about 50 milliamps or so peak. So you could use a 10k in there, and it works. It's just for a bit more longevity, I just reduced it a bit. So that's that. Oh, so I think probably don't need to go through these. I think I've probably gone through these devices. This is the low voltage charge pump. As you can see, it's got this one, the one I chose has actually got a 3 volt out. They've got some with 3.3 volts as well. This is the PIC device that I'm using. I'm using the 18313, and the beauty of this device is that you can get it in a 8-pin dip. There we go. So that's all of our paperwork there. So what I'm going to do now is I'll show you the actual circuit itself. So I've got to be a bit careful here with the old fingers because of the voltage, so I'm going to zoom in as well. So let's see if we can get that nice and... There we go, I think we're in focus, I hope. Okay, so here we've got the 90 volt supply, and there's 3 diodes here, and these are the 3 capacitors and the coil. There we go, this is your boy. So that's how that is. Now the feedback here, if you can see, there's a couple of I think they're 0603 or 0805 resistors just down here to the feedback pin. So this is the 100 volt feedback going back to the feedback pin. Again, please be careful when you're messing around with this, because nobody wants to get their fingers burnt here. So this is the switch that I mentioned. So if I switch the switch off, it just doesn't supply any current to this. But again, please be careful, because there's caps in here, and these caps will still have enough oomph in them. They'll still have 100 volts or so for a minute or two afterwards. So just be careful of that. And then in here we've got our charge pump device, which is in this 0.5mm pitch dual inline package. Never quite sure, this says VSSOP10, so that's the actual package that it came in, and I got a little breakout board here, and the caps and whatnot that we mentioned earlier on. It's 5.1 microfarad caps all down there. They're a mixture of surface mount and leaded. There's a leaded one there. I think the rest of them are all surface mount. Oh, I should just ask one thing. It wasn't on the circuit. I just got a reverse polarization, reverse protection diode on here. It's just a boring Schottky 1 amp diode just here. So if I do if I am stupid and put the power the wrong way around, it doesn't do anything particularly damaging to the rest of the parts here. I learnt that from the last flashing light device that I did. Then on here, this is our PIC. I programmed this out of circuit. I don't really want us to put a programmer into a circuit which might have 100 volts on it, so especially if it's not isolated. The transistor, you might be able to see, is just here, SOC 23 package. That's the 47k resistor. Just here. Let's see if we can not kill myself and whatever. Can we do this side by side? I don't know. Let's have a look. There we go. So this is the 47k resistor here, and just here is the 100k resistor. So all in all, that's our device. This is not a particularly exciting entry to the 2018 Flashing Light Prize. I'm sure there'll be others along in a moment, but it was just to show you how one way of generating 90 volts and flashing at 1 Hz. Thanks very much for watching, and hope you enjoyed that. Thank you.